Well, good morning. Any questions before we get started on the summary from last week? Nothing about the meaning of life. Is it going to get colder? And why can't we win all of our football games, huh? Okay, nothing like that. So we're working in norm spaces now, so we're not just vector spaces, we have a way of measuring distance. And then we've specialized to a kind of norm that when you square it, you get a sum of squares. And so those come from things called inner products. And the amazing thing about an inner product is you can start talking about angles. Now, the only angle that we will be talking about are right angles, but you can even talk about other angles. You can define the cosine of an angle and hence get the angle by using the notion of an inner product. And so our goal has been to make sense of this picture up here where the axes are some abstract vector space. M is a subspace, and it's a collection of vectors that we are using to approximate another point. So in general, M will be constructed from measurements. X is an unknown, and we're trying to come up with our best approximation of X based upon the measurements. And we will define best in terms of minimizing the error between X and its approximation M0. And so the intuition we have from playing in R2, where we know the inner product as X transpose Y, is that the approximation should be a right angle there, that if I put any other line, it's going to be longer than the dotted one I have shown. So that's what we're trying to make sense of, and we're doing it for arbitrary inner product spaces. So we've got a vector space, we have an inner product. The inner product, when it's the reals, are these three rules here. It's always non-negative. If it's zero, if and only if, you get the zero vector. You swap the order and you don't change anything when it's real. If you're working with the complex field and you swap, you take the complex conjugate of that complex number, and then it's always linear on the left. But of course, if you can swap them, in the real case, you get linearity in the right as well. So that's the notion of an inner product. To prove that from that inner product, you actually get a norm, the hard thing to show is the triangle inequality. And to do that, this Cauchy-Schwarz inequality is the key step in establishing the triangle inequality when you use the inner product and you take the induced norm from the inner product. And so often you will see this written as norm of X times norm of Y, because that's what this term is. Then once again, the only angle we are defining is a right angle, or being orthogonal, and that just means the inner product is zero. Okay? And X is orthogonal to an entire set if it's orthogonal to every element of the set. And then the other small result we had, just by expanding out both sides, is that if X is orthogonal to Y, the Pythagorean theorem holds. The norm of X plus Y squared is just the sum of the norms squared. So that's something we'll use again today. Questions on that? Those are the key properties of things you get with inner products. I guess you're happy with that, I'll assume. So here's something we call the Preprojection Theorem, and I'll point out what it's missing in a second. to get the full projection theorem. So here we're dealing with a real inner product space, so we're dropping the complexes. And this is talking about finding approximations to points. So we have a point in an inner product space and a set of approximations, and this set has the property that's a subspace. And the preprojection theorem says that if there exists a minimizing vector, so that's what this means, we've actually achieved the infimum. If there exists a minimizing vector, it is unique. And then the minimizing vector is completely characterized by the error is orthogonal to the set of approximates. It's orthogonal to the subspace. So the approximation error, x minus m0, is orthogonal to m. And that's if and only if. So that's what we want to show this morning, really quickly. Okay? We're good? We're happy? We think this is cool? Almost? Okay. So the thing we're missing from the full projection theorem that we might get to just at the end of today is we haven't shown that there always exists such an M0. So if it does exist, there's only one of them. And if it does exist, it satisfies that it's orthogonal. And if you can find something that's orthogonal, the approximation error is orthogonal, it is a minimizer. But we don't know that there's a vector in M that satisfies this relationship. We won't know that with the preprojection theorem. Just to be clear, whenever we're playing with an inner product space and you see a norm, it is the norm-induced, whoops, there's a half missing here. So I'll put the square on the other side. It's the norm induced by the inner product. Even if you're in R5, where it's not the one norm, okay? So if there's a norm written and we're doing an inner product space, it's the one that comes from the inner product. I know it seems like it's a very obvious thing, but I wouldn't emphasize it if I hadn't had a lot of questions about that, okay, in the past. So heading that one off. Cool. Then let's get going. So, proof of the preprojection theorem. I'm going to do it with two claims. We'll do the hardest one first while we're fresh. So let M0 be a point in M if the norm of x minus M0 equals the distance from x. Question? We're okay? Sorry. If there's a point M0 such that we actually achieve the minimum, then x minus M0 has to be orthogonal to M. Okay, so that's our first claim. If we achieve the minimum, it's necessarily true that it's orthogonal. Okay, so we're going to prove this by the contrapositive. What's the contrapositive? P implies Q if and only if, not Q implies not P. Okay, so we're going to show x minus M0 not orthogonal to M implies the norm of x minus M0 is strictly greater than the distance from x to M. Okay? not orthogonal, that negates Q. And then not equal to the distance means it has to be bigger. It can never be less than the distance, right? So yeah, you can say the negation is it's not equal, but there's only one way the equality sign can be violated. Okay, so what can we get by not being orthogonal? So x minus m0 not orthogonal to M implies there exists a point M, an element of M, such that if I do the inner product of x0 with M, it's not equal to 0. So that means it's not orthogonal. Orthogonal means every point in here is inner product with this is 0, so it's not orthogonal. There must exist at least one point such that this has failed. Okay, now let's just note that we can assume that M has norm 1, okay? If we do x minus m0 and we take M over the norm of M, okay, so we just take M and divide it by its norm, then this thing has norm 1. But what is that inner product? This is just a constant, so I can factor it out. So that's 1 over the norm of M, inner product, x, m0, and M. This is still not equal to 0. Thus, we can suppose that the length of M is 1. So we can just always normalize it. So when we chose our M, we just scale it so its norm has 1. We're going to make use of that. Okay, so now I have this coefficient I'm going to define, beta, is x minus m0, inner product with M, and I know that's a non-zero number. Could be positive, could be negative. I'm going to draw my picture in just a moment, assuming beta is positive. And notice I can assume that if I want, because if beta is negative, then I replace M with minus M, and then beta is positive. But because M is a subspace, if M is in there, minus M is in there as well. So, but it's just not going to matter that much. Okay. So now I'm going to define a new point. M1 equals M0 plus beta, whoops, not beta 1, beta times M1. Okay, so let me see if I can draw a picture. Of what we're doing here. Okay, so that's the only thing I can do well is my subspace. So that's M. This is capital M here. Here's my picture X. So this is where we'd like to choose M0. This is M. This is the vector x minus m0. This is m0. Excuse me. Okay? Now, I don't know m0's on this side or this side, and in general, it's not one-dimensional. I'm just making a picture here, okay? I'm just making a picture so you can see what we're going to do. So this m0 plus beta times m1 is going to be someplace in M. I don't have a green, so let me do this. Okay. This point here is M1 equals M0 plus beta times M1. God, even I don't like the look of that. M0 plus beta times M1. Why am I calling it M1? That's an M, and that's an M. There we go. Now we got it. Okay. I don't want M on both sides. The new point M1 is my original point, and then I'm going to move. What I'm going to show you is a little bit closer. Okay, so the whole idea of this proof is if I'm not orthogonal, I can define a new point that gets me a little bit closer and have a better approximate. Okay, so it's not going to necessarily be here, but it's going to be such that the length of this vector is shorter than the length of this vector. My approximation error is smaller. So let me prove that. Okay. So we're going to look at the norm of x minus m1, and it's always easier to look at its square because then it's done by an inner product. So this is x minus m0 minus beta times m squared. Okay, and so that means it's the inner product of the vector with itself. X minus m0 minus beta m with x minus m0 minus beta m. Okay. Can we see what we get here? I'm going to keep this term grouped together because that's the thing. I'm going to try to show that this length is smaller than this length. So I'm going to keep this term together. So I have this times this. That's going to give me a norm squared. I have this term times this term, and this term times this term. They're the same, so that's twice. And then I have this term and this term. Okay? So x minus m0 with x minus m0 minus 2 beta x minus m0 with m. Okay? Plus the inner product minus beta m minus beta m. So you could put a plus here and move this inside. That's fine if you want to do that. Okay. So what do I end up with? This is norm of x minus m0 squared. That's this one. That's the norm squared. Inner product of x minus m0 with m is equal to beta. Okay. Inner product x minus 0 with m, that's this magic coefficient beta that I used to move along with. So this is minus 2 beta squared. And here I factor out minus beta times minus beta, so I get beta squared. Then I've got the inner product of m with itself, which is 1. Okay, so this is plus minus beta squared. Okay, so now I've only got one beta. Beta is not equal to 0. So the norm of my new approximate is strictly less than the original one that I had. So So it's not a minimizer. Okay, so because beta is not equal to 0, the norm of x minus m1 squared is strictly less so conclusion, M1, M0 is not a minimizer. Okay. See, I've got some puzzled faces. Inner product Z1 plus Z2, Z1 plus Z2 is inner product Z1, Z2 plus 2 inner product Z1, Z2 plus inner product Z2, Z2. Okay? That's all we used up here. That's all we did. Here's our Z1 and beta minus beta m, that's the Z2. And so that's the expansion that we did right here. Yep, question?
I was just a little confused by the step before where, so you have your m naught, which you're assuming is a minimizer, but it's not perpendicular, like the error is not perpendicular. And then you add this, so then there's some m where this m is also not perpendicular to the error. And then you take a step in the direction of that, like the step where you said m1 equals m naught plus beta m. So you don't need to put any, like when you're doing this, you don't have to say that you're actually going in the, like you had said something about that, like you don't have to specify you're going closer to x in this step.
Well, the picture, okay, so the question is, how do I know I'm getting closer or farther away when I move in this direction, right?
You have to say, yeah.
So how do I know I'm getting closer or moving farther away? I mean, this thing could have shot way over here, okay? It could have been pointing in this direction and ended up way over here, right? So, you get your intuition by solving the problem in R2, literally, and you draw yourself a line. Okay? We will shortly start looking at how you take things and you do their projection onto here. So if you just kind of look at that problem, you will get the intuition where this thing comes from. Right now, all I need to show is if it's not orthogonal, then I can find another one where the norm gets smaller. So I could have just written it down and not drawn this picture and just said, this is my M1. Now look, magic. I look at the norm of x minus M1 squared. So there's my x minus M1. And I just expand it using the Z1 plus Z2, Z1 plus Z2 expansion. And voila, I end up at the end that number is precisely equal to this number minus a positive constant. So that number is smaller. Okay, so that shows there exists another point that's where the norm is smaller, so M0 is not a minimizer. M1 is not a minimizer necessarily either. It's just smaller error. Question?
And that's the same reason why we're saying beta is not equal to 0 as opposed to saying it's greater than 0 and less than 0. Be on either side of the orthogonal.
Yeah, when I chose my M, but I could have said beta is positive without loss of generality because I replaced M with minus M. The length is still 1. And then if I put minus M here, I change the sign of beta. And so if beta had been negative, then maybe I'm moving backwards. But this is dimension 406. Really, it may have been moving like this, but I can't draw a dimension, a 406-dimensional subspace in a 916,000 dimensional vector space. I just can't draw it. So you have the impression that I'm moving always along the same line, but I'm just staying in the subspace. I'm just staying in the subspace. So the picture maybe is misleading in that regard. Other questions to help get the doubt out? Okay, other questions to help have more inspiration so that you're more confident? No? We don't really care, so why should we, doubt it or be inspired? Anyway, so this says if I'm not orthogonal, I can find another point that makes the distance smaller, so this is not the minimizer. Okay, so that's claim 1. Let's do claim 2. Claim 2, if I can find a point where I'm orthogonal to M, then M0 is a minimizer, so I achieve the infimum, and M0 is unique. Okay? If M0 satisfies the approximation error is orthogonal to the subspace M, then bingo. Okay, let's prove that. Proof. Assume X minus M0 is orthogonal to M, and let M and M be arbitrary. Okay. So let's compare the approximation error with some arbitrary point to X. Okay. So what I'm going to do is add and subtract, or subtract and add the same thing. Okay, so here's M0 minus M0, those cancel. So X minus M squared is equal to this. Now, M0 is in M is in M, hence M0 minus M is an element of M. Okay, M's a subspace, so if I add two vectors, no problem. Also, we know that X minus M0 is orthogonal to M, so that implies X minus M0 is orthogonal to M0 minus M. Okay, so what do we know about the sum of two vectors when they are orthogonal? Square of the norm is the sum of the squares, okay? So, by Pythagorean theorem, X minus M squared equals norm X minus M0 squared plus the norm of M0 minus M squared by Pythagora, okay? Our nice Greek. Okay, so I want to calculate the distance from X to M. That's by definition the infimum over little m in M. So I'll do the distance squared. Okay? And that's equal to a sum of two things. So norm x minus m0 squared. Right, that's the distance squared there. Huh. So, how does this term change when I vary m? It doesn't. It's independent of m. Okay. And this term, how do I make it the smallest when I search over all points in my subspace? I can make it 0 by choosing m equals m0. Okay. I can't make it any smaller. And if I choose anything that's not equal to m0, then this is positive. So it's a unique minimizer. Clear? Okay. Okay. So conclusion. The minimizing vector is unique and equal to m0. Yay. Okay, so once I have x minus m0 orthogonal to m, the Pythagorean theorem makes it very easy to establish that there's no other vector that gets me anything smaller. So this is the minimizing solution. Oops. Hate it when that happens. I guess that's a feature. Can't be a bug. Okay. Okay, so this is the preprojection theorem. We've got everything shown now. There's only one minimizing vector. If there is a vector that exists, it's unique, and it's characterized by the error is orthogonal to m. So we showed if it's orthogonal, we're fine, we got the minimizing thing, and if it's not orthogonal, I can produce one that has a smaller approximation error. So that's the preprojection theorem. Questions so far? No? Now, where in our proof did we use the fact that m is finite dimensional? We haven't, okay? Only in my picture. That was a two-dimensional. We used the fact that it was two-dimensional to draw a picture, okay? So everything here is true in an infinite dimensional inner product space X, okay? The projection theorem will not say if there exists, it will say there does exist. And then everything else, okay? So here we still don't know whether there exists a minimizing one or not. So the fact is, which is a little deeper than we will get into in Rob 550, in general, when X is infinite dimensional, there may not be a point that achieves the minimum. But when X is finite dimensional, there always exists such a point. And then if you take a little bit more mathematics and study the infinite dimensional case, you'll have things called Hilbert spaces. And for such spaces, when M is closed, we haven't defined what closed means, then you'll get existence as well. So. Okay. We're going to take a little mental break and do the Gram-Schmidt process. Okay, so we have a handout on that. points. Okay. Initial data, we're going to start out with a set of vectors that is linearly independent. Then we're going to recursively compute, oh sorry, I want to call this n, I apologize. V1 to Vn. Such that two things hold. For every 1 less than k between 1 and n, the span of the first k new vectors that I compute is precisely the same as the span of the first k vectors in my set. So I got y1 to yn. Its span up to k will be a k-dimensional subspace because they're linearly independent. I'm going to compute new vectors that give me the same span. So these things are going to be linearly independent if I have k of them and they have the same dimension. So I preserve linear independence. And then, for every I not equal to j, 1 less than I, j between n, the inner product of vi and vj is 0. Okay, so Gram-Schmidt is going to take a basis or a set of linear independent vectors for a subspace. It's going to compute another basis such that I look at the span of y1, that's one-dimensional, span of y2, that's two-dimensional, span of yk, that's k-dimensional. I get exactly the same thing when I stop at 1, stop at 2, stop at k with the new basis. And these are now orthogonal. Of course, I can take each of these vectors and divide it by its own norm, and then I get orthonormal. Okay? So Gram-Schmidt is a way to build orthonormal bases for subspaces or vector spaces in inner product spaces. Okay, so that's what you want to get out of this handout. We go through it. Just a recursive procedure to start out with vectors that are not orthogonal and get another set where they're orthogonal. Well, thank you. Okay. So this is the handout. Everybody brought it? If not, just make a few notes. First stuff is just definitions we've been through, where we've got CNC, RNR, our inner products, real matrices. The inner product is the trace of A transpose B. If we have functions, the integral A to B, so those are a whole bunch of inner product spaces. Cauchy-Schwarz, we've done that. Triangle inequality, orthogonal vectors, this notion of an orthonormal set is when all the vectors are orthogonal and they all have length 1, orthonormal. So Gram-Schmidt will help us build those types of sets. So here's Gram-Schmidt. So my experience is you're very good at reading this and doing it and getting the hang of it. So we'll just go through it at a high level and not do every possible calculation, but just to see how it recursively builds upon itself. So what we're going to do is focus on building the orthogonality, because after the fact, you can just take every one of these vectors and divide by their norm to make it orthonormals. That's the easy part. So how do you make them orthogonal? Okay, so remember, our data is y1, y2, yn linearly independent. So we just set v1 equals to y1. Now we're going to make v2 a linear combination. It's really a linear combination of y2 and y1, but it's very convenient since y1 and v1 are the same to write it like this. And now we're going to choose this coefficient such that these two vectors are orthogonal. That's all it is. We're just going to solve the equation v2, v1 equals 0. And so we plug in for v2, and we use the linearity on the left-hand side. So this is written so that it'll be fine in the complex case as well, though we don't really care that much in this course. But it's written out that way. Okay, so linear on the left-hand side, we get y2 with v1, and we get minus a21, and I factor out the coefficient. So I want to solve this equation equals 0. So if I can divide by this term, then I get this formula right here. Okay. But y1 comes from a linearly independent set, and v1 is y1, so hence this thing cannot be 0. It's part of a linearly independent set. Okay? So this equation makes sense. I'm never dividing by 0, so there's my coefficient. Bingo. And so by construction now, v1 and v2 are orthogonal. And what you want to do is go through here and convince yourself that these two vectors and these two vectors have the same span. Well, v1 and y1 are the same, so we just need to show that v2 is in here, and we need to show that y2 is in here. We already know y1 is in here because it's v1. We already know v1 is in here because it's y1. So it's the new vectors we need to show. Well, v2 and y2, I mean, we just defined, to show one way, here's v2 written as a linear combination of y2 and y1. Bring this on the other side and write y2 as v2 plus this, and you've got it written as this equation. So y2 is in the span of here, and v2 from this equation is in the span of here. So recursively, I've got y1, y2 like this. Now I've got v1 and v2 in the same subspace. Okay, so this is really important how it doesn't change the span when you go through and stop at k. You stop at k, you get the same spans. It's recursively doing that. It's not getting you something new. It's staying in the subspace defined by the first subspace, the second subspace, the third subspace. It's just recursively doing that. This is just one more step before writing down the general solution. You want to produce a vector v3 that is orthogonal to v1 and v2. So you just write it as y3, the new vector you have. You've already done y1 and y2. And you want to see if you can find these coefficients such that this inner product is 0 and this inner product is 0. You might think that you'd have to get simultaneous equations to get two coefficients and two unknowns. The magic thing, by writing it down this way, they decouple. You get A31 by only doing one calculation, and you get A32 by only doing one calculation. So it becomes a diagonal set of equations. So just go home and substitute in V3 and expand it, and then use the fact that I've already have V1 and V2 being orthogonal. V1, the inner product with itself, that's the norm squared, and I just solve for A31, and I do the same thing for A32. And then, am I dividing by 0? And the answer is no. Y1 and Y2 are linearly independent, hence V1 and V2 are linearly independent. Neither one can be 0. So you just prove that you're never dividing by 0 recursively. And then you quickly see what the pattern is, and this is what you want to have written down on a cheat sheet, okay? So. You don't want to waste time deriving that, though you can very quickly. But personally, I always forget the formula and I just sit down and rederive it, okay? Or I go look it up, okay? I hate to memorize stuff, but that's just me. But when I'm taking an exam, remember you guys get one sheet of note, front and back on exam 1, and 2 sheets of notes, front and back, exam 2. So you get plenty of notes. And so as an exercise, I want you to prove this recursive nature of building a basis for this subspace that is now orthogonal. So prove that. The proof is given later in the handout, but it's good practice. Okay, just prove it. And then, is my proof right? Well, read the one that's in the back and you go, okay, yeah, mine seems to be equivalent to that. Questions so far? You see that it should be straightforward to read it and do it, or you think I'm assuming you're way smarter than you really are? Am I overestimating you? No. Please, oh.
Can you just scroll back up so you can see the general formula? Thank you.
Yeah. General formula is step K on page, I don't know, page 5. We're page 5, step K. Okay, the handout's posted. Read through the examples where we just do all of the numbers, okay? So you've got that in the handout. And the inner product space is R3R, where the inner product is just X transpose Y. So get all the numbers. Here's the proof that I said is given later. I'll have you do it. Okay. So now we're on page 8. So make a note. Page 8 has two, well, it has one super cool thing here, okay? So one that's straightforward, but one, they're all straightforward. They're just calculations, but one that you really want to remember. The first one is very useful, and it just uses the linearity of the left or the right sides of the inner product, okay? If you have a vector and it's orthogonal to a set of them, it is automatically orthogonal to their span. Why is that true? Well, something in the span is just a linear combination of these things, okay? So suppose W is a linear combination of these guys. just write it out, and then you're going to get x with these with a coefficient out in front, but x inner product with any of these elements is 0. Okay? So x orthogonal to S if and only if x is orthogonal to the span of S. So write that down in your notes. It's probably a homework problem next week. I forget, I think it is, but if not, you want to know that one. So that's a good one to know. Okay, and so this is the case when S has a finite number of things, but it's true in general, and it's the same proof. This is the one that's super, super cool. If we have a basis that's orthonormal, then calculating the representation of a vector with respect to that basis is just a few inner products. It's not simultaneous equations that you have to solve. Yes. Okay? This is giving you the representation of an abstract vector with respect to an orthonormal basis. And so all you do is you write x as a linear combination of these things, and if you find these coefficients, then you have the representation. And then you just take the inner product of x with individual vectors, and you use the orthogonality until you get down to k and I being equal, and then this gives you 1 because it's orthonormal, and you just pick off the ith coefficient. Okay, so go through this one and convince yourself that this representation is true. So it's just writing down the definition and then realizing that you do not have to solve simultaneous equations. Okay. And then if the basis is orthogonal and not orthonormal, you're going to get a norm of vi squared here. So just do that. So just play with it. And so that's super cool. When it's orthonormal, this is how you get the ith coefficient of the representation. So what is a perfect exam question? Is I give you 5 vectors, okay? And I tell you I only want the third coefficient of the representation. So if you don't know this fact, you're going to set up a 5 by 5 set of equations, right? And it's going to take you an hour to do that problem that's worth 5 points. And if you know this, 1 calculation, you're done, okay? So that's an easy exam question. So you can just pick off even, if I only ask for the third coefficient in the representation, you've got 1 calculation to do. And if they're orthogonal and not orthonormal, divide this by the norm of vi squared. So it's super cool. Yeah. Yeah. So question. What if v, whoops, I got subscripts here. How'd that ever happen? Is orthogonal but not orthonormal. And alpha I is x vi inner product VI with itself. So that's the norm of VI squared. Okay. Okay, so if you don't have the handout with you, we're on page 8, and it's full of interesting things. Make a note. Make a note. Page 8 of the handout is full of fun little facts that you want to play with. Okay, now we're skipping to page 14. So, forget about the reciprocal bases for now. Here's a worked example of doing Gram-Schmidt on functions, okay? So I've got functions on 0, 1. This is a set of continuous functions, real valued. The field is the real numbers. So here's continuous functions on the interval 0, 1. There's the inner product, integrate from 0 to 1. And we do Gram-Schmidt on the monomials. So all the calculations are there, and just some remarks about how you can use the symbolic toolbox to do all of those integrals without doing integrals yourself, okay? So just so that you don't get frightened about doing integrals, okay? So you can just integrate from 0 to 1 of v1 times y3, et cetera. So you can just do Gram-Schmidt, and you can just write down what the inner products are in terms of symbolically, if you want. Okay, so it's a handout's got lots of little practical stuff, and the main thing is what we were doing here. Start out with a set of linearly independent vectors. We produce another set of linearly independent vectors recursively. If I stop at k, I have the same span on both sides, and these vectors are orthogonal. So when I is different from j, the inner product is 0. And then it's a friendly amendment to divide everything by its norm to make it orthonormal. So that's super good, tight summary. We're good? Gram-Schmidt, you can go out, figure it out? No. Nobody wants to give me any positive feedback today. Okay. I think I'll start writing the exam this weekend. That way I've got lots of time to come up with some gnarly problems, okay? So you got a month to make me feel good, okay? Okay. So I want to get to the proof of the real projection theorem, but I need a couple of intermediate facts. So back to linear algebra. Okay. We could have done these several weeks ago, but I think we were kind of getting bored with linear algebra, and we wanted to start seeing things that are closer to being new to us, which is these best approximation problems. So now we got to go back, though, and get a couple of little facts. And here's the first one, proposition. Let XF be a vector space of dimension n. Okay, no inner product right now. This is just back to linear algebra. We're not doing inner product spaces. I mean, it's true in an inner product space because then you have a vector space, but this is true more broadly. If K is at least equal to 1 and strictly less than n, and I have a set of vectors, vk. Just does that so you guys can catch up with your writing, okay? So I have some number that's less than the total dimension, and I've got k vectors that are linearly independent. Okay? So if then I can always find n minus k vectors that are linearly independent. Then there exist these guys such that I now look at v1 to vk, vk plus 1 all the way to vn is a basis. That's really ugly. It's a beautiful thought expressed in ugly handwriting. Okay, this is how this result is always stated. If I have a set of linearly independent vectors, I can always complete it to a basis. Okay? Any set of linearly independent vectors can be completed to a basis. Okay, why is this potentially important? Well, our vector space has dimension n. I know I can find a basis for it. It's finite dimensional. But who says I can find one that includes these vectors that I've already worked really hard to produce and have some special properties that I really, really like, okay? Who says if I like these vectors, I can always make sure that my basis contains them, okay? Who says that that's true? That's not a property of just a basis existing, that it has to include the ones I like, okay? Maybe it only includes the ones you like, not the ones I like, okay? So this says, if I work really hard to make a really useful set of vectors and they're linearly independent, I can build a basis that includes those vectors in it. Okay, so proof is, as you would guess, by induction. Okay. We establish a cute lemma that will allow you to do the proof by induction. Okay, so I'm going to essentially do k implies k plus 1. And then you guys just write down the base case. You'll have the k plus 1, and then you'll do your proof. Okay, so here's the cute lemma. XF, a vector space n-dimensional. One less than k, strictly less than n. V1 to Vk linearly independent. Then there exists a vector we'll call Vk plus 1 in X. Such that this set is linearly independent. Okay, so I can always add one more. So you guys see how the proof by induction goes, right? I can add one more, then I can add two more, then I can add three more. Eventually I can add up to n minus k more, and then I filled up my vector space. Okay? You want us to do the proof, or you want me to just leave it to you? Gulp. Oh. Okay, how do you think the proof goes? How do you think it goes? I mean, I need to show that such a vector exists. Now, unless I know a lot about how to guess that vector, so when we did the preprojection theorem, I started out with something that I didn't think was the minimum, and I produced something that got us closer to being at a minimum, okay? I actually produced it. I showed there exists another one. So that was cool. That was constructive, okay? That was constructive. So if I just have k vectors, how do I produce another one? That seems hard, right? So what's the other way then to, instead of doing it as a direct proof, what's another way to attack it? Sorry? You can do contradiction or contrapositive, okay? Both of them will work in this case, okay? So you show that if there doesn't exist one, there's a problem, okay? So, so that's the idea. I mean, if I'm going to do P implies Q, then I need to actually construct this one. If I do not Q implies not P, I say if this thing doesn't exist, there's a problem, okay? So that's essentially contradiction or contrapositive. Okay, so I'm going to do contrapositive. So P implies Q if and only if not Q implies not P. Okay. So what is P? K is less than N. V1 to Vk linearly independent. Q, there exists Vk plus 1. Linearly independent of V1 to Vk. Okay? So what is not Q? Well, there doesn't exist one, yes, I know, okay? But what's another way to write not Q? I'm just trying to have you think through the proof here. For every other vector I choose in X, it is linearly dependent on these guys. And how do I write dependence? You do the coefficients. What's the more elegant way of doing that? No, it's perfectly right, okay? Use the word span. Okay, so not Q is for every X in X, X is an element of the span of V1 to VK. Everybody agree that that's cool? And it's a lot easier than writing down coefficients. Okay, it's a shortcut, the notion of span. Okay, so it's okay. Every X I choose is a linear combination of these. Okay. So now, what does it mean that every X is in the span? Well, X has to be a subset of those vectors, right? Because every X is in there. Now, the dimension of X is then upper bounded by what? K. Okay? So then, n equals dimension of X is less than or equal to dimension of V1 to VK. Whoops. Okay, so these guys were linearly independent, so it's actually equal to K, but I don't really care. And so this gives me not P. K strictly less than N, not is, okay, is that K is greater than or equal to N. And that's what I have. Okay, so conclusion, K is greater than or equal to N, which implies not P. Okay, I'm spending more time on this than I really wanted to, but on the other hand, it's interesting today. We've done two different types of existence proofs. One was constructive. I had my subspace, my angle wasn't a right angle, and I guessed a vector that got me a smaller approximation error, and I proved it by using some inequalities, okay? I guessed it and I proved it. This one, I had no clue how to guess a V that was linearly independent of these. And so I turned the problem around. If I can't find it, there's a problem that this set must already be a basis, okay? K has to already be equal to N. So it's just to give you some proof strategy. You guys always want to know strategy. I say, well, how do I know I do an end around versus throwing the ball down the field, okay? It's strategy, it's practice, it's knowing the situation, it's a little bit of luck, okay? It's experience. So that's it. How we doing? Okay. Okay, so back to inner product spaces. So I have X, have F equals R or C, I don't care. And I have an inner product. Definition. Suppose S contained in X is a subset. Then S perp is what it's called. is the set of all points in X such that X is orthogonal to S. Okay? This is called the orthogonal complement of S. Okay, so S might just be array, and this is everything orthogonal to it. Okay. Exercise 1. S perp is a subspace of X. Okay, so I don't care if S is a subspace or not, its orthogonal complement is always a subspace. So it contains 0, that's clear. 0 is orthogonal to everything. Okay, 0 is orthogonal to everything. So the orthogonal complements everything that's orthogonal to it. And this one is good practice. S perp is equal to, if I take the span of S and I take its orthogonal complement, I get the same thing as if I just took the orthogonal complement of S. Ooh. Okay, let me write down one thing, and then I'm going to ask you to prove it at home, and then we'll do the proof. Okay? Let X, F equals R or C be an inner product space. And finite dimensional. M contained in X be a subspace. Then X can be decomposed into a direct sum of M and its orthogonal complement. Whew. Okay? If you think about it geometrically, it makes total sense. Okay. And remember, the direct sum means the intersection has to be the 0 vector. Well, if X is in here, little x is in here, and little x is in here, then X is orthogonal to itself. So it has to be the 0 vector. Okay, so. So the direct sum part is easy, but can I always write X as everything that's in M plus something that's orthogonal to M? So that's what we'll look at on Thursday. So, and that'll allow us to complete the proof of the projection theorem. So, thank you for your attention. Hope you had fun. If you did, I couldn't tell it. Okay, you hit it really well. I know.